In this section 3.4, we'll be talking some more about the conditional statement. And what we look at first is we talk about variations of conditional statements. And so if we consider the statement P, it rains, and the statement Q, I take my umbrella, the direct conditional statement is if P, then Q, or if it rains, then I take my umbrella. If we reverse the order of the antecedent and the consequent, so we have if Q then P, or if I take my umbrella then it rains, that is called the converse. The inverse is where we insert nots in front of each of the antecedent and the consequent. So it would be if it doesn't rain, then I don't take my umbrella. Finally, in this case, the contrapositive is where we switch the order of the antecedent and the consequent and also insert negations. And that would read, if I don't take my umbrella, then it doesn't rain. Now, it turns out that either the converse, the inverse, or the contrapositive is equivalent to the direct conditional. Take a moment and look back at the examples I have given you for if it rains, then I take my umbrella, and see which one you think is equivalent to the direct conditional. While you're doing that, I'm going to correct my table here that, again, the journal has messed up. But I'll fix it. So hopefully you've decided which one you think is equivalent. Is it the converse, the inverse, or the contrapositive? Pick one of the three. Okay, now what I'm going to do is I'm going to create our truth table. Remember, for the two statements to be equivalent, we have to have the same truth value. So if true, then true. If true, then false. That's the case that's false. If false, then true. And if false, then false. So what we're looking for is we're looking for this arrangement of truth values. So now the antecedent is Q and the consequent is P. So if true, then true would be true. If false, then true would be true. If true, then false would be false. And if false, then false would be true. Well, we can see the order has changed, so that's not it. This is our direct, and this is the converse. So let's do our negations of P and Q. Okay, P first, now Q, false and true. Now we're doing the inverse. Let's see if that's equivalent. Okay. So we want to do if false, then false would be true. If false, then true would be true. If true, then false would be false. And if true, then true would be true. And comparing it to our direct, again, we see they're out of order. So the converse is not equivalent, nor is the inverse. What we do note, however, is the converse and the inverse are equivalent. So that means it must be the contrapositive. Let's check and make sure. So the antecedent this time is the not Q. There's our antecedent. And our consequent is the not P. So if false, then false is true. If true, then false is false. If false, then true is true. And if true, then true is true. And we see, yes, this does turn out to have the same truth value as the direct conditional. So, it says the direct conditional statement is equivalent to the contrapositive. And based on our truth table, we also see that the converse and the inverse are equivalent. Okay. Now, we have other ways of saying the conditional statement besides if P, then Q. Of course, our primary way is to say if P then Q. You can also leave out the word then. If P, Q, that means the same thing. P implies Q, means the same. P only if Q. P is sufficient for Q. Now, what I always tell my students to do is to learn the ones where the P and Q come in the opposite order, and then all of the others, P comes first and then Q. So necessary is one case where Q comes first. The consequent comes first. All P are Q, we've worked with that before, and Q if P. This one's kind of a dead giveaway because of the if in front of the P, but I want to show an example because I think this one is one that gives a lot of people some trouble, and of course this one below it. So I've tried to come up with an example that would kind of give you an idea of that all of these are saying the same thing. If you take Algebra 2, then you passed Algebra 1. If you take Algebra 2, you passed Algebra 1. Taking Algebra 2 implies that you have passed Algebra 1. You can take Algebra 2 only if you have passed Algebra 1. Taking Algebra 2 is sufficient, and this is one of the ones I think is hard, for having passed Algebra 1. And I think it makes sense when I look at this particular example. Now, here's one where it's reversed. Passing Algebra 1 is necessary for taking Algebra 2. All Algebra 2 students have passed Algebra 1. You have passed Algebra 1 if you are taking Algebra 2. So all of those mean the same thing, and I wanted to illustrate that those words are equivalent. Okay, last of all here we have the biconditional. This is the statement if and only if. And what you'll note about the biconditional is it has a double-headed arrow. And what the biconditional is it's equivalent to two if-then statements. It's equivalent to if P then Q and if Q then P. And of course my table got messed up again, and I'm a little bit like Monk. I go crazy if things aren't lined up. So there, I'm going to straighten it out for us. Okay, so what I want to do is create the table for what it actually means. It means if P then Q and if Q then P. So we're going to have our four cases, alternating true, false, true, false. If true then true is true. If true then false is the one case that's false. False then true, and if false then false. Now we're going the other way. This time Q is the antecedent and P is the consequent. So if true then true is true. If false then true is true. If true then false is false. And if false then false is true. Now we have to have both of these. So true and true, false and true, true and false, true and true. Since they mean the same thing, what that means is that we get the truth values for if P, if and only if Q from the previous column. So what we note about this is that if both are true or both are false, we end up with a true statement. On the other hand, if we have one true and one false, the biconditional is false. So let's look at some examples. We're going to talk about the truth value of these examples. Obama is president if and only if McDonald's sells hamburgers. Well, this is true, and this is true. It's an if and only if. They're both true, so our statement is true. All right, 4 plus 9 equals 49. That's false. If and only if 56 equals 65. That one's false. Both of them false. We end up with a true statement. And I think that's the one that's easy to get tricked up on. All right, Germanna is a community college is true. If and only if 2 plus 9 is 29. That part is false. True if and only if false is false. So in order for a biconditional to be true, both P and Q have to be true, or both of them have to be false. Next thing you want to do is watch the example or sample problems that I'll do for section 3.4.